Welcome back to Talk Tensors. Ready for another deep dive?
Always excited to dig into some fascinating research.
Well, get ready, because today we're taking on a paper with a pretty catchy title.
Oh, yeah.
Benchmarking graph representations and graph neural networks for multivariate time series classification.
A mouthful, but definitely a topic worth exploring.
Absolutely. And what makes this paper particularly interesting is its focus on comparison.
Right. Instead of introducing a brand new algorithm, it sets up this head-to-head competition between different approaches.
Exactly. It's like saying, okay, we've got all these different ways to use graphs for classifying time series data, but which ones actually work best?
It's all about finding the most effective tools for the job.
So before we dive into the competition itself, let's break down some key concepts.
Sure, what do you want to start with?
Let's start with multivariate time series classification, or MTSC for short.
All right, so imagine data that changes over time, like let's say your heart rate or the stock market.
Okay, I'm with you.
And this data has multiple variables being tracked at the same time.
Makes sense.
So MTSC is all about using this data to categorize something based on those multiple changing variables.
So like my Fitbit uses MTSC to figure out if I'm walking, running, or just lounging on the couch.
Exactly. It analyzes your heart rate, steps, and other data to classify your activity.
But the paper argues that traditional methods for MTSC haven't been so great at capturing the relationships between these variables.
Right. Think about it. Your heart rate and sleep patterns are probably connected somehow, and capturing that connection could be crucial.
For accurate classification.
Exactly. And that's where graphs come in. They're really good at representing these relationships.
Okay, remind me how graphs represent those relationships.
So picture each variable as a node in the graph.
Yeah.
And the connections between them are called edges.
Gotcha.
So if your heart rate and sleep patterns are strongly correlated, the edge between those nodes would be stronger or thicker.
Ah, so it visually represents the strength of the connection.
Precise.
Now, I'm really curious how they set up this benchmarking arena to test these different graph approaches.
Well, they started with a diverse set of data, 26 data sets to be exact.
Wow, that's a lot.
It's from a well-established archive called the UEA MTSC archive.
Okay, and what kind of data does it cover?
A pretty wide range, actually, from classifying heart rhythms to recognizing human activities.
So they're covering their bases.
Exactly. It ensures they're not just testing on one very specific type of data.
Makes sense. So they've got the data. What do they do next?
They focused on the building blocks of graph representation, nodes and edges.
Okay, so for the nodes, they experimented with 3 ways to define their features, right?
Yep, essentially what information each node holds.
So like option 1 would be to just use the raw time series data for each variable.
You got it. Sometimes the simplest approach works surprisingly well.
Makes sense? Keep it simple.
But they also tested some other options that involved transforming the data first.
Oh, like what?
One was calculating the differential entropy.
Differential entropy. That sounds complicated.
It's actually a measure of how unpredictable a signal is over time.
Okay, so like a flat line has low entropy.
Exactly, and a really jumpy signal has high entropy.
Gotcha. So they're basically seeing if adding that measure of unpredictability helps with classification.
Precisely. And then they also tested calculating the power spectral density for each time series.
Okay, now that one definitely sounds complicated.
Think of it this way. Imagine you're looking at a sound wave.
Okay, I can visualize that.
The power spectral density tells you how much power the signal has at different frequencies, like breaking it down into its components.
I see, so it gives you a different perspective on the data.
Exactly.
Okay, so those are the node features. Now what about the edges, the connections between the variables?
Right. For the edges, they explored 4 ways to define those connections.
Okay, and each one represents a different kind of relationship.
Yep. The first was a simple, complete graph where every node is connected to every other node.
I see, so that's like the most basic starting point.
Right. It's a baseline to see what happens when you don't consider any specific relationships.
Makes sense. What were the other approaches?
Well, next they used Pearson correlation, which basically measures how much 2 variables move together.
Like height and weight, right? Taller people tend to weigh more.
Exactly. That's a strong positive correlation.
But what if the relationship is more nuanced than just a simple correlation?
That's where mutual information comes in.
Okay, and what does that measure?
It captures any kind of shared information between 2 variables.
So it goes beyond just a linear relationship.
Precisely. It can capture those more complex dependencies.
And then there's the most intriguing one, adaptive edge learning.
Right. This is where the model learns the best edge connections during training itself.
So we're not predefining the relationships. The model figures it out on its own.
Exactly. It learned which connections are most important for the task.
Okay, that's pretty cool.
It is. And that brings us to the last piece of the puzzle.
The graph neural networks,
You got it. The GNNs. They tested 5 different types.
which are basically like different engines for processing this graph data.
Exactly. Each with its own strengths and weaknesses.
So the big question is, after testing all these different combinations of nodes, edges, and GNNs,
Did they find a clear winner?
exactly, what did they find out?
Well, that's where things get really interesting.
All right, I'm on the edge of my seat, but I guess we'll have to wait until after the break to find out.
You got it. We'll be back in a flash to dive into those results and see what they mean for you. All right, are you ready to dive into those benchmarking results?
Definitely. Spill the beans. What do they find out after putting all those combinations to the test?
Well, the first big takeaway, and maybe a little surprising, is that there's no one-size-fits-all solution.
Really? So there wasn't a single magic combination that always worked best?
Nope. No single combination consistently outperformed all others across all datasets.
So it's not as simple as saying adaptive edge learning always wins or GCNs are the way to go.
Exactly. The optimal approach depends on the specific data you're working with.
Interesting. So what worked well in some cases, but not in others?
Well, sometimes the simplest approach, just using the raw time series data as node features, worked surprisingly well.
Huh. You'd think those fancy transformations would always give you an edge, right? The differential entropy and power spectral density stuff.
You'd think so, but sometimes those transformations actually made things worse. It all comes down to understanding your data and choosing the right tools.
So knowing your data is key, even more so than just picking the most sophisticated algorithm.
Absolutely. And that leads us to another interesting finding. How you define the edges in the graph, those relationships between variables, matters a lot.
Speaking of edges, how did adaptive edge learning perform? Where the model learns the connections itself.
Well, that's where things get exciting. Adaptive edge learning was one of the most consistent top performers.
So it seems like letting the model figure out the relationships on its own can lead to some real improvements.
Exactly. It's like we're moving away from handcrafted features and toward more flexible, data-driven approaches.
Which makes sense, right? Let the machine do what it does best.
Precisely.
Now, you mentioned earlier that the choice of GNN architecture wasn't the most critical factor, but were there any interesting findings in that area?
Actually, yes. Remember Megit, the GNN that uses those multidimensional edges?
Yeah, I remember that one.
Well, it consistently outperformed the regular GAT network, especially when those transformed node features, the differential entropy and power spectral density were in play.
So if you're using those complex node features, it makes sense to use a GNN that can handle those richer edge representations.
Precisely. It's all about finding the right combination of tools.
This is all incredibly insightful, but I have to ask, all this benchmarking was done on data sets with equal length time series, right?
Right.
But what about real world scenarios where time series have different lengths? Think about patient health records. Some people have years of data, others have just a few months.
That's a fantastic question, and it's one of the limitations the paper acknowledges.
So they basically set up a well-controlled experiment. But now the challenge is to see how these findings translate to the messier, unpredictable real world.
Exactly. The real world is rarely as neat and tidy as a research data set.
So the next frontier is figuring out how to adapt these approaches to handle varying time series lengths.
Absolutely. That's where things start to get even more interesting.
I can imagine, and that's what's so exciting about this field, always pushing the boundaries.
Right. Always new challenges to tackle.
Speaking of new challenges, are you ready for some novel notions?
Hit me with them. Let's hear those wild ideas.
Yeah, let's get those creative juices flowing.
Okay, so the paper's focus on data quality got me thinking, what if we could develop a system that not only identifies the optimal graph representation for a data set,
Yeah.
but also explains why that representation is the best in a way humans can understand?
Whoa, that's ambitious. It's like having an AI consultant for your time series data.
Exactly. Imagine you feed in your data and it tells you, use differential entropy for node features, adaptive edge learning for the edges, and a GCN architecture for the GNN because your data has strong frequency domain patterns and complex relationships.
Okay, that would be incredible. It would take out so much of the guesswork.
Right, and it would build trust in the results because you understand the why behind the choices.
But how could we even begin to build such a system?
That's the million-dollar question. It would require a deep understanding of both graph theory and machine learning, plus some sort of explainability engine on top of that.
Hmm. Maybe we could leverage techniques from automated machine learning or auto ML, which already does this for model architecture and hyperparameters.
Right. AutoML could be a good starting point. And for the explainability piece, maybe we could borrow ideas from symbolic regression.
Symbolic regression.
Yeah, it's where algorithms try to find mathematical expressions that fit the data.
Ah, I see. So the system not only finds the best solution, but it also tells you why it's the best.
Exactly. Like writing a guidebook to help you understand those complex decisions.
I love that analogy. And this system wouldn't just be useful for researchers, right? Think about businesses and organizations.
You're absolutely right. It would democratize access to these powerful techniques.
A small business owner could use it to analyze customer data. A doctor could use it to personalize treatment plan. So many possibilities.
Exactly. The potential applications are vast.
Okay, we've officially entered the realm of science fiction, but that's what Novel Notions is all about, right? Pushing the boundaries.
Precisely. And who knows, maybe one of these wild ideas will spark the next big breakthrough.
Well, on that note of boundless possibilities, I think it's time to shift gears and delve into the history of time series classification.
Sounds good to me. Let's take a step back and see how we got to this point.
All right, take us back to the early days, before deep learning and fancy GNNs. How did people approach this problem?
Imagine a world without powerful computers. Researchers had to rely on some pretty clever techniques. One early approach was measuring distances between time series.
Distances. Like how far apart they are on a graph.
Not quite, more like measuring how different their shapes are.
Okay, give me an example.
Well, they use something called dynamic time warping, which aligns two time series to account for differences in speed or timing.
So if you have two time series that are stretched or squeezed differently, dynamic time warping tries to find the best way to align them.
Exactly. It's like trying to match up two rubber bands that have been stretched and twisted in different ways.
Yeah, I can picture that. So they'd compare these warped time series to see how similar they are.
Right, and use that to classify them.
Clever. But it probably had its limitations.
It did. It struggled with things like time series of different lengths or with a lot of noise.
Makes sense. So what came after rubber band warping?
Well, another approach focused on finding characteristic patterns called shaplets.
Shaplets. What are those?
Imagine you're looking at a bunch of heart rhythm recordings, and you notice a specific squiggle that always appears before a particular type of arrhythmia.
Okay, so it's like a fingerprint for a certain event in the time series.
You got it. Researchers developed algorithms to automatically find these shaplets and use them to classify new time series.
Sounds like a powerful technique, but probably computationally challenging.
You're right. Finding those shaplets could be like searching for a needle in a haystack.
So distance-based methods and shaplets were the main players for a while. Then what happened? What shook things up?
Well, you already know the answer. Deep learning came along and revolutionized the field.
Ah, deep learning. The game changer.
Exactly. Suddenly we had these neural networks that could learn complex patterns without us having to handcraft features.
I bet those neural networks were a big deal for time series classification.
Oh, absolutely. Techniques like convolutional neural networks, or CNNs, proved incredibly effective.
But aren't those typically used for images? How do they work with time series data?
Think of it like looking at a musical score instead of listening to the song. The score represents the notes and rhythms over time. It's kind of like a visual representation of music, and CNNs can scan through that score, looking for patterns.
I see they're analyzing the patterns over time, just like they would with pixels in an image.
Exactly.
So CNNs made a big splash, but where do graphs and GNNs fit into all of this?
That's the key question. CNNs are great at capturing temporal patterns, but they weren't so great at capturing the relationships between different variables in a multivariate time series.
Right, they can see patterns in my heart rate over time, but they might miss how that's connected to my sleep pattern.
Precisely. And that's where graphs and GNNs come in. They provide a way to represent those relationships explicitly.
So we've gone from rubber bands and needles in haystacks to complex networks of connections.
That's a great way to put it. And the paper we're talking about sits right at the forefront of this new wave of research.
Which makes their benchmarking work even more important. It helps us figure out which approaches are most promising.
Absolutely. It gives us a roadmap for future research.
But before we get too serious, I think our listeners are ready for another dose of speculation.
You know it. Time for Novel Notions, round 2.
All right, let's hear it. What's your most audacious idea this time?
Okay, let's imagine we're not just classifying time series data.
Okay.
What if we could use GNNs to generate new time series data that fits certain categories?
Wait, you're saying we could train a GNN to be like a composer writing a symphony in the style of Beethoven?
Exactly. Think about the possibilities: generating synthetic medical data for rare diseases,
Wow.
creating realistic simulations of financial markets, even composing music, or generating video game environments.
The potential is mind-boggling. But wouldn't there be massive challenges in making sure the generated data is actually meaningful, not just random noise?
Of course.
Ugh.
And we'd need to be very careful about potential biases and ethical implications, especially when dealing with sensitive data.
Right, so it's a wild idea, but it's a wild idea with huge potential impact.
Exactly. It's all about pushing those boundaries and exploring what's possible.
And who knows, maybe one of our listeners will be inspired to pursue this research and turn these wild ideas into reality.
That would be amazing to see these conversations sparking real-world innovation.
Well, on that note of inspiring possibilities, let's wrap up this deep dive with a final round of novel notions before we say goodbye.
Sounds good to me. What do you have in mind for this final round?
Well, this time I want to shift gears a bit and explore the human side of things.
The human side. I like it. Tell me more.
We've talked a lot about the power of GNNs for MTSC, but what are the implications for us as humans? How do these advances in AI change our understanding of ourselves?
That's a really interesting question, one we don't often consider.
Right. For example, if a GNN can accurately classify different emotional states based on physiological data, does that change our understanding of emotions?
That's a deep question. It makes you wonder, does it make emotions more objective, less subjective?
Right. It's like we're used to thinking of emotions as these internal experiences, but what if AI can reveal patterns and connections that we're not even aware of?
It's a whole new way of looking at ourselves.
And it goes beyond just emotions. Think about health diagnostics. If a GN can analyze your medical history and predict health risks, does that change your relationship with your body?
Does it empower you, or does it create more anxiety?
It's a double-edged sword, right?
No.
Incredible potential. But we have to be careful not to over-rely on these technologies.
Absolutely. We need to have these conversations to think critically about the human impact.
You're right. It's not just about the algorithms. It's about the implications for our lives and our understanding of the world.
Couldn't agree more. It's about using these tools responsibly and thoughtfully.
And that leads to another thought. As GNNs become more sophisticated, will we need new ways to visualize their findings?
That's a great point. Graphs and charts might not be enough to convey the complex insights these models can provide.
Maybe we'll need to invent entirely new forms of data visualization, maybe even interactive experiences.
Imagine a virtual reality environment where you can walk through the connections in your own medical data.
Whoa, now that's a wild idea.
It is. But it shows how the way we interact with these models needs to evolve as the technology advances.
This has been a mind-blowing deep dive, and I feel like we've only scratched the surface.
There's always more to explore. That's what makes this field so fascinating.
Exactly. There's always more to learn, more to discover.
And who knows what incredible breakthroughs await us in the future.
Well, on that note of boundless possibilities, we'll wrap up this episode of Talk Tensors. Thanks for joining us on this journey. And keep exploring those dense jungles of research. You never know what gems you might uncover.
Happy exploring. Sounds good to me. And for this final round, how about we flip the script a bit?
Flip the script. Intrigued. Tell me more.
Well, we've spent a lot of time on the technical side of things.
Right, all those algorithms and benchmarks.
Exactly. But for this last round, I want to explore the human side of all this.
The human side. Okay, I'm listening.
We've talked about the power of GNNs for MTSC.
Right, how they can uncover these complex relationships in data.
Exactly. But what are the implications of that for us as humans? How do these advances in AI change our understanding of ourselves and the world around us?
Wow, that's a big question. I like it.
For example, if a GNN can accurately classify different emotional states based on physiological data.
Like heart rate, brain waves, that kind of thing.
Right. Does that change our understanding of emotions? Does it make them more objective, more quantifiable?
That's a profound thought. We often think of emotions as subjective experiences, but what if AI can reveal patterns and connections that we weren't even aware of?
It challenges our assumptions, right?
Absolutely. And it's not just limited to emotions. Think about health diagnostics.
Oh, yeah, that's a huge area.
If a GNN can analyze your medical history and predict potential health risks with high accuracy,
Potentially life-saving information.
it could be. But does it change your relationship with your own body?
Right. Does it empower you to take more control of your health? Or does it create anxiety, a feeling of being constantly monitored?
It's like a double-edged sword. The potential benefits are incredible, but we have to be mindful of the potential downsides as well.
We can't just blindly embrace these technologies without considering the broader implications.
Exactly. And that's why these conversations are so important. We need to think critically about how these advances in AI will shape our future, both individually and as a society.
It's not just about the technology itself, it's about how we use it and how it impacts our lives.
Couldn't agree more. And it leads me to another thought. As GNNs become more sophisticated, will we need to develop new ways to visualize and communicate their findings?
That's a fantastic point. The traditional graphs and charts we use might not be enough to convey the complex insights these models can uncover.
Right. We might need to invent entirely new forms of data visualization, maybe even interactive experiences.
Imagine a virtual reality environment where you can literally walk through the connections and patterns in your own medical data, or see how your emotions map onto a 3D landscape.
Wow, that's an amazing idea. But it makes sense. As the technology evolves, the way we interact with it needs to evolve as well.
We need to find new ways to bridge the gap between the complex computations happening inside these models and our own human understanding.
And who knows, maybe these new forms of visualization will lead to even deeper insights and discoveries.
It's an exciting frontier, full of potential.
This has been an incredible deep dive, and I feel like we've only just begun to explore the vast landscape of possibilities in this field.
It's a field that's constantly evolving, which is what makes it so captivating.
Exactly. There's always more to learn, more to discover, and more to discuss.
And we can't wait to continue these discussions with you on future episodes of Talk Tensors.
Well, on that note of boundless possibilities, we'll wrap up this episode of Talk Tensors. Thank you for joining us on this incredible journey into the world of graph neural networks and multivariate time series classification.
Thanks for listening, and as always, keep those curious minds engaged.